Okay, class, we're going to start with the explanation of the light reaction. And the first time you hear this, it's going to be confusing. And you're just going to have to probably hear it more than once before you understand. I'm going to go through all the slides and what the slides say. And then I will make a separate video of just the overview of the light reactions. So let us begin. In the thylakoid membrane, so thinking of those little stacks, right? In the membrane of the thylakoid is a protein that looks like this that we call a photosystem. So we have two photosystems in one thylakoid membrane. It's photosystem 1 and photosystem 2. In these proteins are embedded with them chlorophyll. So we have pigments and chlorophyll A. So when we talk about light reactions, the first thing we need to explain to you is that a lot of chemistry, like we talked about before with oxidation or induction, has to do with electrons and electrons being moved from one atom to another atom. Another thing that can happen with electrons is that they can jump inside the atom. And in doing so, that gives off some energy. So a photon here is light, and light gives off photons of energy. So one photon of light hits a chlorophyll molecule. It excites the electron. The electron jumps up or is in an excited state. And then it's going to lose energy and fall down back to its normal level, which is called the ground state. When it falls down, it will give off heat and a photon. So here is a photosystem. And the idea of the photosystem is that your photon of light hits the top chlorophyll, the one that's exposed to the sunlight outside. It excites the electrons, and then the electrons jump back down to the ground state, but they give off that photon, which excites the next pigment, and then gives off a photon, excites the next pigment, and a photon excites the next pigment. A photon excites the next pigment. A photon, it hits, there are two chlorophyll A molecules. So we're just kind of looking at one side. So that chlorophyll A on this side gives off one electron up to the primary electron acceptor. The primary electron acceptor is just a chemical that steals the electron. It's an electron stealer. That's the way you want to think about it. So it takes it away from the chlorophyll A. Now, notice this side never shows anything, but note that this side does the exact same thing. The light is going to hit the top one. It's going to excite all the way down. An electron's going to go here, and then one electron up. So the two chlorophyll A molecules are going to lose two electrons to the primary electron acceptor. Okay? So language 2, the chlorophyll A is being oxidized because it's losing electrons. The primary electron acceptor is being reduced because it's gaining electrons. All right? So the next step is that the primary electron acceptor passes its two electrons to another protein, and then to another protein, and then to another protein, and then to another pair of chlorophyll A. So this protein right here, these three proteins are called the electron transport chain because it's like transporting electrons. When it does that, we're going to get ATP made because we're also going to actively transport hydrogen ions from the stroma into the thylakoid. And so that's going to then help make ATP. So this is going to help the chemoosmosis that's going to happen over here. So because the electrons are falling downhill, it's a way that we're going to be able to make ATP. All right. Step 4. Light in photosystem 1, that would occur at the same time it happened in photosystem 2, moves, excites the electrons that were in the chlorophyll A, jump up to the primary acceptor. This primary acceptor now is going to give it to a different molecule, a molecule called NADP+. Now, NADP+ accepts 2 electrons, so there's the little holes right there. Those are supposed to be the 2 electrons, and also will bind to a hydrogen ion, or also called a proton, to make NADPH. NADPH is going to be important for the Calvin cycle. So this is like going to go off and do the Calvin cycle. Just think of NADP+ as the Uber driver, because it just carries electrons and hydrogen ions over, and then it drops them off and it comes back. So it's not really totally reacting. All right, so here's that picture in depth. Again, we have light exciting the chlorophyll molecules. It makes the electron jump from the 2 chlorophyll A molecules to the primary acceptor. The primary acceptor gives those electrons into the electron transport chain. Then those 2 electrons get put into the 2 chlorophyll A molecules over here. They jump up to the new primary acceptor in photosystem 1, and then those electrons are given to NADP+, and off they go to the Calvin cycle. So I like this drawing because it just is a graphic of, it took energy, which is a photon, to jump the electron up. The electron going down the hill allows for energy to be made. And then a photon of energy jumps it back up to the top and then off through NADPH. Now, if we had this happen, it would happen once and stop, because after that one time it went through, the chlorophyll A molecule wouldn't have any electrons left. So photosystem, this whole thing would just stop after one time through. But it doesn't. How come it doesn't? Well, that's because that plant needs water, and water is around this whole photosystem. So what happens is that when the chlorophyll A molecules lose electrons, they, in turn, steal electrons from water. Thieves, right? It's all about electrons and stealing and taking away. So the 2 chlorophyll A molecules are going to steal 1 electron from one water and 1 electron from another water. So it actually takes 2 waters. And when it does that, we will then have 4 hydrogen ions, or 4 proteins made, 4 electrons, those are getting stolen by the primary acceptor, and 1 oxygen molecule. So oxygen is going to get made, and we're going to get protons and electrons. So water in this story is what we call split. We split the water, okay? And this is just showing you 1 electron. So if 1 water molecule steals 1 electron, then really you make half an oxygen, and then you make 2 protons. So all of these pictures always just show 1, but the other side is going to. So now oxygen is a waste product. So when it makes the oxygen, it is a waste product. So off it goes. It just gets released through the membrane. It travels through the membranes and out. All right. The next step is we're going to be making ATP. How are we going to make ATP? We're going to make ATP by chemiosmosis. Chemiosmosis is where we move hydrogen ions down their concentration gradient across the thylakoid membrane, and that helps us make ATP. So there are 2 sources of the hydrogen ions. 1, when we break down the water, we made hydrogen ions. And 2, ATP is first produced by the electron transport chain because it is pumping hydrogen ions from the stroma into the thylakoid. So the hydrogen ions create a concentration gradient inside the thylakoid. So this is what we're talking about here. Here's our electron transport chain, and the energy that is given off by these electrons as they go down allow for this middle protein to pump hydrogen ions or protons into the thylakoid space. Okay, so it's pushing them in. The water is being split and also making hydrogen ions. And so what ends up happening is now we have what we call a concentration gradient, which just means that there are more hydrogen ions on this side than that side. Okay? So, because we create this concentration gradient, hydrogen ions are naturally going to want to go back over here and make it even. That's what diffusion is all about. It's the natural order of the universe. They always want to be spread out and even. So these hydrogen ions will then travel through this protein called ATP synthase. And when it does so, it actually makes the protein spin. And there's a molecule of ADP out there, and there's also some phosphate out there in the stroma. And when the hydrogen ion passes through, ADP plus phosphate is going to make ATP. So because of this concentration gradient, we can make ATP. The electrons that are traveling through the electron transport chain help pump hydrogen ions into the thylakoid space. The splitting of the water adds the hydrogen ions to the thylakoid space. Now there's more here than out there, so it will then diffuse through ATP synthase and make ATP. So in the end, we have made ATP and we have made NADPH. And both of those are going to be used for part 2, the Calvin cycle. So let's look at this one more time. One more time. We have light hits the chlorophylls. It bumps the chlorophylls down, excites the chlorophyll A, electron jumps up to the primary electron acceptor. Those electrons then get passed through the electron transport chain. While they're being passed through, hydrogen ions are being pumped through the electron transport chain from the stroma into the thylakoid space. Those electrons continue on, are passed to these two chlorophyll A molecules. These two chlorophyll A molecules jump up to this primary electron acceptor in photosystem 1, and then those electrons are passed on to NADP+ to make NADPH. Water is split at photosystem 2 to add electrons to this whole system. And in doing so, oxygen, a waste product, is created, and hydrogen ions are created and are filling in the thylakoid space. Because we have hydrogen ions pumped through and hydrogen ions made from the splitting of water, we now have more hydrogen ions in the thylakoid space than in the stroma. So this higher concentration gradient of protons are going to now pass through ATP synthase, a special protein. And as it does, it makes it spin. It takes an ADP molecule and a phosphate and attaches it, creating ATP. And so in the end, we have waste product of oxygen and we have the product of NADPH and ATP in the stroma, ready to go on to the Calvin cycle. So I do want to just point out we're talking about one of these little thylakoids. So we're looking at it like from the side. Here it is, like the little photosystem 2, photosystem 1, and ATP synthase. So this is just one thylakoid. So one thylakoid, actually, you can see actually the ATP synthase is on the other side. Photosystem 2, photosystem 1, and ATP synthase. This is one thylakoid, so it can only do one set of these. That's why we have many thylakoids. So after all of this, the ATP and the NADPH is going on to the Calvin cycle, and then the waste product product of oxygen is released. So water is used in the light reactions. Light is used in the light reactions. The light reactions create ATP, NADPH, and oxygen.